Okay, I'm hoping this is working. Oh, it didn't look like it was. All right. Here we go. Number 2. What are we on? Part 5 now? Gosh, sorry, I didn't mean this for this to be so long, but I guess more information is better. They want us to calculate the first, some of the first 8 terms of each one of these series, and then compare them. How they different, state as many, blah blah blah. Now, of course, I'm not gonna make you do that on the test, but it's good to think about. Okay, so 2/3, 4/3, 6/3, 8/3. I'm guessing, would this be 12/3? No, wait, 2, 4, 6, 8, 10. Oh, wait, what? Is that a misprint? 10/4? You gotta be kidding me. 2/3, 4/3, 6/3, 8/3. Life is going pretty well. All of a sudden, 10/4? I'm guessing that's probably a misprint. Can we just say for a second, again, this is not very test-like. Another not test-like thing you shouldn't be able to do is edit your test. I'm really sure that they meant thirds here. I mean, one of these things is not like the others. Let's be honest here. Okay, so 2/3, 4/3, 6/3, 8/3, 10/3. Great. This looks to me like an arithmetic sequence. So I'm going from 2/3 to 4/3 to 6/3. This, as I'm going down this thing, I'm adding 2/3 the whole time. If you just see the first 2 terms, you don't know. It's like maybe it's doubling, 2/3 to 4/3, and then, oh, okay, wait, I didn't double again. What, 6/3, 8/3, and then I think there's a mistake here. Okay, so we have this plus 2/3 arithmetic sequence. So, series. So I want to use the arithmetic sum of series. Of course, it's finite. We don't have such a thing as arithmetic infinite, but arithmetic finite, it's this one. So that's the one we're going to go for here. I need to know what n is. They tell me they wanted 8 for all these. Circle. 8/2 times 2. That's just in concrete in that formula. A sub 1 plus n minus 1 times the common difference, the thing I'm adding each time. Here, that's positive 2/3. A lot of people messed up on the quiz, and this thing was supposed to be negative, and they put it as positive. That's going to make a huge difference when you add them up. If the terms are going up, but the terms are going down, huge difference there. I don't have a lot of room down here. Maybe I should just have done this down here. Anyway, let me do that in the calculator. Gosh, can I do that in one step? 2/3 times 7. Then what am I doing? Plus 4/3. I'm working from the back end there. That's 6 times 4. Times 4. That would be 24. Okay. Actually, it would be nice maybe to see all these here. I can write the similarities down, stuff down here. 2/3, 4/3, 8/3, 16/3, 32/3. Okay, this is what I was talking about in the first one. Here, as I'm going down the line, I'm not adding the same thing every time. It turns out I'm actually multiplying. This is times 2/3 as we increase. So that is a geometric one, my friends. Geometric ones require this formula to add up a finite, here it's list of 8, geometric items. So, S sub 8 equals G sub 1. Yeah, maybe I'm going to write it wrong. Times 1 minus R, that thing that's happening. Oh, wait a minute. I'm not multiplying by 2/3, you idiot. Gosh, why didn't someone tell me? What am I multiplying by each time? I'm multiplying by 2. Glad I caught that before I got into big trouble here. Why did I catch that after I said that? Wow. There is hope for me. Okay, so double, 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 double. This is the doubling sequence. So the R here is 2 to the n power, which is 8. Some people are accidentally putting n minus 1 there. I can see why, but nope, in that formula, and you have this staring at you, it's just good old-fashioned n right there. Okay, over 1 minus r, which is in the end going to be negative 1. All right, 2 to the 8th power. Oh, man, I don't remember that. I should, but I don't. I want to say 500. Nope, 256. 256. So we have 2/3 times 1 minus 256, which is negative 255, divided by negative 1, which would be positive 170. Okay, this is positive 170. Great. Okay, and the last one, 2/3, 4/9, 8/27, 16/81. Okay, what's going on here? 2/3. If I'm adding something, okay, that's really weird. So is that one. This kind of looks like, since the top's going 2, 4, 8, 16, the bottom's going 3, 9, 27. It looks like I'm multiplying the top by 2 and the bottom by 3 each time. Another way to say that is here's the one. I guess I was just foreshadowing. Oh, see, that's what it was. It was foreshadowing, kids. This is multiplying by 2/3 every time. Just check that. 16 over 81 times 2/3. Yeah, sure. Okay. So it's another geometric one. Well, I've already talked about the similarities. G sub 1 times 1 minus r to the n over 1 minus r. Okay, 2/3 to the 8th power, 2/3 to the 8th. That gross thing, I want to take 1 minus that. Times 2/3. I'm going to divide that by 1/3, basically. Divided by 1/3, which is the same as times 3. So this whole thing turns out to be 1 point bloody bloody blah. Is that a nice fraction? Probably is, actually. Yeah, it is, because we've got this enormous power of 3 on the bottom, and should be an enormous power of 2 on top, actually. But I don't think that is. What happened? What did I do? 2/3, 2, 2, 2, 16. Oh, maybe there was some reducing that happened in there eventually. Anyway, that's what I got. Oh, and dividing by this makes it weird. Okay, so we have, I'm going to say 1.92 if no one minds. It's approximately 1.92. I thought maybe the fraction would be a little nicer than that, but not quite. Oh, and we're adding them up. That's what makes it weird. Okay, so it's not exactly 1.92, but something along those lines. Okay, so what's the same about these? Well, 2 and 3 are geometric. All of these have their a sub 1 or g sub 1, whatever we're going to call it. We're all 2/3. That's a similarity not to forget. What else? 1 and 3 had a constant thing going on. It was 2/3. In 1 it was add 2/3, and 3 was multiply by 2/3. I don't know how you'd say that. D here equals R here. I don't know if that's really significant. What else? They were all adding 8 terms. They're different because, well, here R is double, here R is 2/3. Oh, here we go. In the first two, A sub 2, or the second term, is actually the same. And 2 and 3, the numerators seem to be the same. Well, you notice 2, 4, 8, the sequence of numerators here and the sequence of numerators here. You just kind of go looking. But really, in terms of the calculation of this, the only thing that would matter when I look to what types of questions I'm going to ask on the test, the similarities and differences, the things that you'd care to notice in these kind of things is, okay, which ones are geometric, which ones are arithmetic, what's a sub 1, what's r, and what's d, and which ones of those things are positive and negative, and which formula do I use and how, basically. That's about all you need to think about for that one. Alright, number 3. What is the meaning of all this notation? The limit as n goes, well, I'll just read it to you. The limit as n goes to infinity of 1 minus n over 2 minus n. This, when they're not doing a summation here, they're not talking about a series, they're just talking about what happens to this term, this 1 minus n over 2 minus n as n goes to infinity. What happens to each separate sort of instance of this, as we have 1 minus a zillion over 2 minus a zillion? That might look better to people if we did it this way. Negative n plus 1 over negative n plus 2, that's the same thing. We have sort of negative zillion over, plus 1 over negative zillion plus 2. And really, how different are those two things? Well, really not a whole lot different at all. They're both very close to negative ginormous over negative ginormous. As they get more ginormouser and more ginormouser, yes, I just said that, the 1 and the 2 become insignificant compared to the power of the negative zillion. So this starts to look like 1 in my mind, but let's see what they say in part B. Maria says the value of the expression is half. If you agree, justify her statement. Well, I don't. I think it looks more like 1. If you disagree, find the correct value. One trick they like to use in these things is you know what, the other thing I don't like about this is the fact that it's negative n plus 1, negative n plus 2. We could multiply top and bottom by negative 1, and it would look a little bit nicer as n minus 1 over n minus 2. All these things are equivalent, because I'm multiplying top and bottom of the fraction by the same thing. Here I didn't actually multiply it by stuff. I just rearranged this. 1 minus n is the same as negative n plus 1. Multiply everything by negative 1, multiplied by -1 over -1. That's like multiplying by 1, and you get this version. N minus 1 over n minus 2 I think is a little easier to digest, sort of. N minus 1 over n minus 2, then the next tricky thing to do to sort of reduce this in limit language, that's equivalent to dividing everything by n. I can divide the top and bottom by n, and I think it's been a while, people might forget this. If you divide top and bottom by n, what this turns out to be is 1 minus 1 over n, and 1 minus 2 over n. Now, we talked about this back when we were first talking about limits in 8.2, I think. 1 minus n, what's kind of nice about that 1 minus n business is the limit, this is one of the first ones we talked about, the limit as n goes to infinity of 1 over n, as n starts to get huge and huge and huge, this whole thing blows up and becomes 1 over 6 trillion. That is going to look really close to 0. So in stuff like this, and 2 over n is really the same thing. 2 divided by 6 zillion is 0 also. So again, as n starts to get huge and huge and huge and huge, we really just kind of think of this as turning into 1 minus 0 over 1 minus 0. It's going to 0 a little bit slower, but I mean, they get really close to 0 really fast, which in the grand scheme of things is 1. If you don't believe this, you could put this in the calculator, 1 minus x over 2 minus x, make a table, jump way down the table. You'll start to see that it's going to approach this, but it's never going to quite get there. All right. Okay, I think you could just about teach an entire course about number 4. This could go on and on and on. Pascal's triangle is so rich in the number of patterns that have been found in it. There's probably lots of patterns that haven't even been found yet. It's crazy. Let's talk about what really is most relevant for this. Again, I'm not going to ask such an open-ended question in this test. Kind of impressive to know this stuff, and it would help you depending on what classes you took after this. But anyway, the 5th term in the 30th row. Okay, let's talk about the 30th row. The 30th row starts out as 30C0. The next term is 30C1, and 30C2, etc. So the 5th term, and this is actually, we would call this the first term. And the first term's got this 0 here. So the 5th term, being careful about that, the 5th term would be 30C4. That is actually what we would refer to as the 5th term. And the value of that is 27,405. Okay, I'm sure if I did that on the calculator, that would work out. 30C4 is this 27,000 unit. List as many facts as you can that lead directly from this statement. Well, if I know that the 5th term in Pascal's triangle is this. I know that if I have a group of 30 things and I choose 4 of them, there's 27,405 ways to do that. Other things that I would just know from combinations, like the 5th term in the 30th row should be the same as the symmetrical spot at the other end of the row, like 30C0. Oh, sorry, 30 would equal 30C0. 30C29 equals 30C1. So eventually, if I count back correctly, I'd find another one that's equivalent to this, and that would be 30C26. That one equals this as well. I know that 30C4 is the sum of the 2 items above it in Pascal's triangle, which would be the row up here, which would be 29C. Well, think about that. 29C0 is here. 29C1 is sort of kitty corner above the 1 like this. So this would be 29C4. It's the sum of 29C4 and 29C3. I don't know. Again, you could go on and on and on about this. I'm thinking of the most important ones that I'm going to hold you responsible for, or that you're going to wish you knew. And it's this sort of summation thing down the table, the fact that there's symmetry in the row, and the fact that when you're finding the 30th row 5th term that it's 30C4 and not 30C5. It's sort of one less than the number of the term. Alright, I believe this is the last thing in part C, so it'll be good to stop after this one in this video because I only have about a minute left. Write a mathematical statement that describes the relationship between NPR and NCR. For what values of N? Okay, we talked about originally talking about how NCR we defined as, well, take the permutation and divide by how many ways there are to rearrange each permutation, and you get the permutation when you don't care about the rearrangements. For what values of N is your statement true? Well, just about all of them. We know in the first place that N has to be greater than R or equal to R anyway, just for NPR and NCR to even be defined. N and R both have to be bigger than or equal to 0. I can't think of any other places where this isn't going to work. Sorry, I had a little video glitch here. Here's the definition of NPR. NCR then is just, we'll take that and divide that by R factorial. Now we're talking about NCR. If I divide this one by r factorial, I have to divide this one by r factorial too. And we also now have the definition. If n equals r, this all works out fine, because then these two things would be the same. NCR would be 1. 0 factorial turns out to be 1, so there's no problem with any of that. I think this is true for any of these values that would also be defined on NPR. All right, that's the end of Form C.